Okay, so this is the final video regarding solids, liquids and gases and particles. So we're going to consider first pressure in gases. So you are most familiar probably with pressure in gases if you've ever blown up a balloon, and then once you've tied it, you've tried to sort of, if you've ever tried to sort of squash it with your hands, not too hard so it doesn't pop. Also, if you've got a bike, and if you've ever had to pump up the tires, or you've had a flat tire, then pressure of the gas pressure is very important to that. So if we look at this model here, this sort of animation of a gas, we can see the particles are all spaced far apart. We can see them moving around, some are moving very quickly, some are moving slightly less quickly. Sometimes they hit each other, that makes them move slower or faster. But what we're interested here when it comes to the pressure of gases is the fact that they are hitting the walls of the container. Okay, so if you look around the walls of the container here, if you look around the black box, you can see that the particles are hitting those walls, and that is what's causing the pressure. All right, that is what why there is now a pressure being exerted in this container. So remind ourselves that in a gas, the particles are moving quickly, they're moving randomly, they often bump into each other, but there is generally a lot of space between them. But they also bump into the walls of their container, right? We can see that in that animation now, still at the bottom of the screen. And when they do, that's what causes pressure. That's why we get pressure in gases. So, got to think about how we could increase pressure. So all of our questions here are about increasing pressure. You have to think that if we wanted to decrease it, we'd be considering the opposite. So what we've got here is we've got two illustrations. Okay, the dials here telling us the pressure in the container. So the container number 1 here, the one on the left, that has a pressure of 2. And container number 2 has a pressure of 4. So the pressure in container number 2 is twice as large, or is double the pressure in container number 1. Now there is only one thing that's different between them. If we're going to ever make a choice or a decision about what causes something, we can only ever have one independent variable. There can only be one thing that's changed. And then we have our dependent variable, which is the thing that we measure, which here is the pressure, so we are measuring the pressure. And then everything else has to be controlled, has to stay the same, so that we know it's only the thing that we've changed that has caused the change in the thing that we're measuring. If you compare those two images, try and think about what's different between them. Okay, so have a think about what's different between them, and then have a think, and then try and make the leap as to what then is causing the increase in pressure in the container on the right. Okay, so the thing that's different between them is if we compare the left-hand side with the right-hand side, there are a lot more particles in the right-hand side. So simply putting more particles in the same volume, so that's something that's controlled, that's something that's the same, that's the volume that the gases particles are in. By having more particles in the same volume, we are increasing the pressure. So more particles in the same volume means increasing pressure. This is what happens when you pump your bike tire up. Once your bike tire is basically the shape it's going to remain, you might keep pumping. The pressure increases. You can feel it if you're trying to press down the tire with your thumb or something. But what you're doing is you're getting more air particles into the same volume, and that's increasing the pressure. But putting more particles in isn't the only way we can increase the pressure. If we look at the second one here, so we can see that one has a pressure of 2 and container 2 has a pressure of 4. So again, the pressure is double in container 2. If we think about what's different between them, so maybe pause the video, have a think. What's different between them? What do you think is causing an increase in pressure? So thinking about our controls, what we're controlling, whereas on the previous example we had a different number of particles, we have got the same number of particles on both sides. But what is different is the volume. We have now got that same number of particles in a smaller volume on the right hand side. So If we decrease the volume, we can increase the pressure. So everything else is kept the same, but we decrease the volume, we increase the pressure. And our final example, so again, on the left-hand side, we've got a pressure in our container 1 of 2, and on the right-hand side, we've got a pressure of 4. Have a think about what's different between them, and therefore what's causing this increase in pressure. And just pause the video, have a little think, and then we'll look at the answer. So let's start by considering what is the same. So the volume's the same, so we haven't changed the volume. And the number of particles is the same. We haven't changed the number of particles. What you see is different is the length of these arrows here. And what they are there designed to show is the speed or the energy of the particles. So we are making the particles in container 2 travel much more quickly than the particles in container 1, and that is causing an increase in pressure. Now, how can we make the particles move more quickly? So think back to earlier. How was it that we could make the particles move more quickly? We could do that by increasing the temperature, by heating them up. So another way we can increase the pressure in gases is to heat the gas up. So we increase the pressure, we can do by increasing the number of particles, by decreasing the volume of the container, or by increasing the temperature so that the particles move faster. Equally, we could reverse all of that. So we could decrease the pressure by decreasing the number of particles, by increasing the volume of the container, by decreasing the temperature. So here we focused on increasing pressure, but just remember that decreasing pressure would be the exact opposite of what we've considered here. So there's a summary. I'm not going to talk it through. It's got the images, but you could just pause the video if you wished and just read through it. But that summarizes what we've just looked at. Okay, so finally we're going to look at diffusion. So if someone in your house has ever sprayed aftershave perfume, a room scent, something like that, you haven't been stood right by it, what you've hopefully discovered is that not long afterwards you've been able to smell whatever it is that's been sprayed. But it hasn't necessarily been sprayed towards you, it hasn't been sprayed on you, it's taken a little bit of a time to reach you. Another example is maybe you're upstairs and somebody's cooking downstairs, and eventually you can smell that cooking. Think about how that smell has reached you. Well, the way it's happened is thanks to this principle that we're going to look at now, called diffusion. So this example is, the idea of opening, I don't know, like a scented bottle. So each one of those green particles would be the scent, and you can see that they sort of spread out and they basically fill up the entire space. Just another example. So just going back, what we're looking at here is a gas. So we're looking at the blue gas particles, and those scent particles would also be gaseous, so they're just sort of spreading out through the room. But equally, diffusion can happen in a liquid. So we could put some red dye in some water, maybe just put it in the corner to begin with, and what we would find out over time is that red dye had sort of spread through the entire liquid. And this is without you stirring it, by the way. This is just happening of its own accord. So key thing about diffusion, firstly, is that it can happen in liquids, it can happen in gases. It's about particles being able to spread out, but it can't happen in solids. All right, so it's not going to happen in solids. That spreading out that we saw on those pictures, that's what we mean by diffusion. It's the spreading out of the particles so that they sort of reach everywhere, in effect. Another way to describe it is, or an important way to describe it, is that the particles are spreading out from where they are more concentrated to where they are less concentrated. That's a really important way of thinking or phrasing diffusion. So it's the movement from an area of high concentration to an area of low concentration. So if you look at the image in the bottom left, what do we mean by concentration? We mean there's a lot of particles in a given volume, okay, and low concentration, there are not many particles in a given volume. So if we look at then the image on the right, we are starting off by putting a drop of whatever it is, a dye, into some water, for example. We have an area where the dye is to begin with, which we would say was an area of high concentration, and then much of the rest of the container is an area of low concentration. I mean, there's no dye whatsoever. But if we allowed enough time, we would see those particles spread out from that area of high concentration to the areas of low concentration, to a point where it was all sort of evenly or equally spread out. So that's an important way of thinking or describing diffusion, about saying that particles go from an area of high concentration to an area of low concentration. So we're going to look at a sort of simulation to sort of help explain why that happens or how that happens. Okay, so the example here talks about water and dye. And what I would say is we can think of this simulation as being about liquids, or we can think of it about being gases. The principle is going to be exactly the same. So this is the particles in the water. I mean, it's not a brilliant model because they should really be, you know, taking the shape of the container and everything. But it's so maybe it's probably better to think of this as a gas. But whatever, the particles are moving in random directions. They're moving around. So I'm going to click the dye in the top left-hand corner. Okay, so when I click there, you're going to see lots of sort of red particles appear. They're only going to be in that top left-hand corner. So that's going to be an area of high concentration. Then let's see what happens over time. Okay. So as we can see, those red particles are now spreading throughout the container. They're certainly becoming less concentrated, and we can see the diffusion happening. So pretty much now, they are sort of evenly spread out through the container. Now what's interesting about this is it happens every time we do it. So let's do that again just to show. I'll just put it in the middle this time, but the same thing will happen. Now this is happening, we know it will always happen, diffusion will always occur, and yet the reason it's happening is because the motion of the particles is completely random. So we have random motion of particles, and yet we have an outcome that we can predict. That's quite incredible. Now to show you that the motion is random, I'm going to click this trace a random molecule, and what we'll see is it'll leave like a little path. It's going to choose one of the molecules, and it's going to leave, it's going to allow us to see the path that it's traveling in. So you can see here that dotted line is the path that red particle is traveling in. It's completely random. Where it goes is all dictated by how it's hit by different particles, by the blue particles, or even by red particles. We can see that motion is random, and yet we can see that diffusion, the spreading out from an area of high concentration to low concentration, always takes place. Okay, let's do it at a really low temperature, and let's see about what happens then. So because it's a low temperature, the particles are moving more slowly than they were. Maybe it's difficult to tell whether diffusion has happened more slowly than before. I'm not sure, but I think if we now compare it at the highest temperature, then hopefully we might see a difference in how they diffuse. So let's do that. So I have it on a really high temperature and press play, and now I'm going to put the particles there, and I hope what you can see, or what you can take from this, is that diffusion happens more quickly at higher temperatures. And the reason it happens more quickly at higher temperatures is because the motion of the particles is much faster. So there's more collisions, and the more collisions means the more random sort of knocking, the more sort of dispersion dispersal of the particles that we get. So I hope that was a useful sort of animation showing diffusion. So it happens, like we saw in that simulation, it happens because of the random movement of particles. So even though it's something we can predict will happen and will happen, it's because of something that's very random. If we increase the temperature, then diffusion happens more quickly, and we'll get it whenever gases or liquids mix. So like putting your red dye into water, or opening your perfume bottle, or spraying your perfume in a room. And then the diffusion will continue to take place. That spreading out will continue until the concentration, about how many particles there are in a certain volume, is essentially the same everywhere. So if you leave your dye in your water, eventually it will look as though the colour, whatever the dye is evenly spread throughout the entire liquid. And that's the end of this entire topic. So we've had 4 videos. We've looked at solids, liquids and gases and their properties. We've looked at changes of state. We've looked at the particle model. We've looked at how the particle model explains the properties of solids, liquids and gases, and how we can understand changes of state in terms of the particle model. We've looked at pressure in gases, and we've looked at diffusion, and all of these have been in the context of particles. So if you have any queries, please let me know.